Да, Святослав, пока мы, вот, так сказать, организационный момент. Смотрите, у нас, значит, будет час лекция и еще одна, последняя, вот как я планирую. То есть дальше вот я хочу, чтобы вы делали ваши презентации, и, так сказать, мы все в один раз не успеем, поскольку людей много. Вот, и надо как-то распределиться, кто это сделает, соответственно, ну, в первую неделю и вторую неделю. Сейчас там какие числа я точно сейчас могу посмотреть. Сейчас у нас...
Здравствуйте.
Здравствуйте, да. Я вот организационный момент сначала чуть-чуть обсуждаю. Сейчас мы начнем. То есть у нас будет, смотрите, 4-го, да, последняя лекция, вот через неделю. И дальше вот 11-18, следующие 2 субботы. Вот я ожидаю, что вы будете делать презентации. Ну, соответственно, просто надо распределиться, кто будет 11-го, кто 18-го. Вот. Ну, я не знаю, я напишу еще общее письмо. Ну, в крайнем случае, я, так сказать, просто директивно это могу сделать, конечно. Но если у вас есть пожелания, значит, в какую дату лучше вы сказали. Лучше раньше, конечно, потому что, ну, я еще раз говорил уже, что это презентация, это, ну, хотя это, так сказать, составляющая оценки зачета, но, в принципе, это мы вот все еще можно поправить, исправить и так далее. То есть постарайтесь подготовиться вот все-таки уже к... Нет, подождите, простите, 18-го мы уже, наверное, не можем, нас просили к 16-му закончить, да? Сейчас, я посчитал. Значит, следующее это у нас 4-е, да? Нет, все правильно, да. 11-е и 18-е. Ну, сейчас одну секунду я еще проверю сам себя. Так. Да, 11-го и 18-го. Все правильно, все правильно. И, значит, уже крайнюю дату я установил, по-моему, 21-го я уже вам написал. Так что уже давайте, да, с вашими, так сказать, готовьте презентации. Ну, собственно, я и всем это говорю, кто меня посмотрит в записи. И, в общем, мы уже будем, так сказать, близиться к завершению. Я надеюсь, будет интересная работа, интересное обсуждение. Так что это будет, надеюсь, не скучно. Okay, so now we I begin my lecture. So today's lecture will be on actually, in a sense, classical topic. So in historical order, we actually finally on the dates about 100 years old. So it's say 10th and 20th of 20th century. Last time we began to talk about David Gilbert's work in Foundation of Geometry, and we discussed his work first published in 1899, Foundations of Geometry, which is extremely influential until today, because it's provided a pattern of what is axiomatic theory, and it's still very much alive. So say today's axiomatic theory are more or less modeled after this Gilbert's example, even if there are some interesting, say, more recent developments, some related to category theory, homotopy type theory, and the New Foundation. So there are some interesting developments. However, that still remains classical in the sense, or orthodox, if you like, right? Because this is what is actually taught in universities everywhere as a standard model for axiomatic theory. Okay, but today I actually take a bit broader perspective, and let me share my screen. Yeah. Can you see the board?
Yeah.
Yeah. So the topic is what is usually called foundational crisis in mathematics in the beginning of 20th century. That somehow comes from German, this kind of descriptions. So in German it was called, okay, I stop my video, just allow myself to write. So it was called Grundlagen Streit. I think it's right. So it's a dispute over foundations that took place, or Grundlagen's crisis of foundations. And in every, say, textbook or any systematic book on this history of mathematics of this period, you will find a distinction. Okay, now I switch back to English. It's distinction between three major positions, one of which is called logicism, and it's represented by Frege and Russell as a major problem. There are some, say, less important figures. I only give you kind of Wikipedia knowledge, right? Then, say, formalism, represented by Gilbert, and usually he just quoted alone. Even as a matter of fact, there are, of course, a lot of people who were influenced, who somehow followed this program. And intuitionism. Originated in the work of Lutz and Brouwer, Dutch mathematician. Brouwer. Okay, so this is a little bit, of course, a simplification of really complicated theory. So if you really begin to look into historical documents and trying to understand these debates, you immediately find that this classification is too rough to approximate. There are a lot of interesting intersection. Yes, please.
You mean there were three sides of this Grundlagen Streit?
Sorry, no, those are three positions, say, right? Yeah, they are not actually quite on equal footing, even if you read there, they are, right?
So, I don't understand what is the difference between logicism and formalism.
Yeah, I explained. There is interesting and actually essential difference. Actually, there is even this formalism, intuitionism is more often opposed. And indeed, there was historically, so in a sense, that was the major event of all this crisis, is a dispute, a controversy between Gilbert and Brouwer. However, there are interesting interconnections. So in a sense, their position were, in certain respects, very different, but in certain other respects, actually similar, right? Actually, I will just in a minute show you a paper, recent paper of 2007, which I really recommend you by living and the active logician, mathematician Per Martin-Löf, who is inventor of Martin-Löf type theory with dependent types. And he's now resigned, but still very active in the University of Stockholm. Right, and the paper title is Gilbert Brouwer Controversy Resolved. So he reviews later developments, including his own contributions, and actually he thinks it's resolved. Okay, even, no, at least it's kind of mathematically resolved, even say philosophically, there are still a lot of differences. And no, actually, when we talk about foundations of mathematics, there are different ways to talk about foundational mathematics, and there are different notions of foundations, and probably I will not spend a lot of time on that. However, at least if we talk historically about this sort of foundations, right? What is interesting that it's really kind of mixture. So on the one hand, it's say new mathematics, at least in the second and third case. But also in Frege, for example, rather it's new logic than new mathematics. But anyway, right? So there are, say, mathematical contributions, and there are some, no, I actually prefer in my research to call these things motivations, right? Philosophical motivation. So there is kind of philosophy behind it. So you may think about logicism or formalism or intuitionism also as philosophical positions, philosophical views. No, even as I thought, if you look, so it's kind of a really mixture of mathematics and philosophy, which I think is very interesting, right? No, so I use the scheme even if it can be criticized, but actually it's still, it's good for teaching, and it's not only, how say, it was not invented later. Actually, this controversy between formalism and intuitionism was described by Brouwer himself in his paper of 1912, where he actually introduces these terms. Yes, logicism actually didn't check. I'm not sure Frege described himself as logicism. You know, there is always, for example, when people talk about analytic philosophy and continental philosophy, I don't know if you really came across, but in history of philosophy, 20th centuries, and even today is kind of fundamental distinction. But then you see that, say, analytic philosophy was self-description, was a kind of manifesto, while continental philosophy was invented by some professors much later, just to refer certain kind of sorts of philosophy, okay? And so we should be accurate, we should distinguish between kind of self-descriptions, right, and later descriptions. No, anyway, I think just if I have a very limited time and it's supposed to give you at least some hints to a lot of contents and materials, it can be useful, even a rough scheme like this. Yes, I propose we actually start with Gilbert, so with formalism, because we already did something. Actually, formalism, at least today, it does not refer quite to the same kind of thing we discussed last week, right? Because yes, it's say there is very interesting exchange of letters between Frege and Gilbert, published, by the way, in English also, where Frege describes, yeah, and that exchange concerns this early work of that I discussed last week, right? Foundations of Geometry. So they already apply, they say it's formal, blah, blah. However, it's not formal in the same sense in which is actually assumed when people talk about formalism. So let's tell me more things about Gilbert. And actually, yeah, maybe some general information about Gilbert somewhere. Wait, opened Wikipedia article about Gilbert. So I think it's quite right that he was probably the most important mathematician of the time. You see, he lived a long life, you see, from 1862, so he's a 19th century person in a sense, but he lived until in the middle of the war, actually, in 43. I think the other comparable figure was Henri Poincaré in France. No, unfortunately, we don't have much time to talk about him in this course. So he was extremely influential, as I already mentioned, in year 1900, when it was second Congress of Mathematicians in Paris. He delivered kind of plenary lecture and presented his famous collection of 23 problems, some of which are resolved, some remain open, some other, by the way, such as continuum hypothesis problem. I think it was even number 1, if you can check. Some people believe it's closed, but some others believe it's still open. So it's still interesting. It's not fully outdated. Anyway, yeah. No, actually, this formalism refers to what may be described as kind of second stage of this foundational project, right? And it is, or otherwise, it's also widely known as a Gilbert program. You can Google Gilbert program and you'll find the reference immediately. So what is Gilbert program? No, I can actually refer to my book on axiomatic method, or to even better to my dissertation, which is more recent. So I revised some of things. So it has a chapter on Gilbert. It's available on university webpage, on my webpage. Yeah. Actually, Gilbert himself described this kind of shift from this early axiomatic pattern to what he did later, what became Gilbert project, as a need of axiomatizing logic, right? Because as I described, or you can look into it yourself, and you can read a lot of secondary literature, of course, to the foundations of geometry, right? There is no formal logic there. So it's formal in the sense which I tried to explain, right? Roughly, that we can exchange points to beer marks according to the language, and this kind of thing. So there we already have this idea that we have kind of core uninterpreted theory, which would later become, say, just syntactic core, right? Just syntax, which needs to be interpreted in one way or another. And that allows to, say, plurality of models. For example, we may have, say, axiomatic theory of Lobachevsky geometry, and then play with different models. As you mentioned me, you studied this half disk model, or some other model, just arithmetical model. Yeah, so all this kind of setting is there already, even in maybe some underdeveloped form. However, there is no formal logic, right? Formal in the sense of being symbolic. Again, you see here, the terms actually are very vague. If you look precisely, they're changing. This notion of formal logic was introduced by German philosopher Trendelenburg in the mid of 19th century, who actually opposed Hegel and such people and tried to kind of revive Aristotle, basically, right? So he talked about formal, but that's history, of course, but it was not symbolic. But today, when we say formal methods to formalize something, right, we expect that the logic itself is formalized, right? It's symbolic, not just formalized in some sense of logical form, whatever it might mean, right? However, in form of precise symbolic calculus, right? And that was something new. So that was a new step. No, even if in some public talks, Gilbert himself tended to stress rather continuity. Even I think it was a big leap, right? By the way, there is very interesting critique by a philosopher who worked a lot on all these things, who died several years ago, unfortunately, Jaakko Hintikka. So he very much opposed this very idea of axiomatization of logic. He thought that it's just misunderstanding, right? Axioms shouldn't be logical axioms. However, what actually, after all, Gilbert meant by logical axioms, those were what we today would call tautologies, right? So the axiomatization of logic, so-called, that we find in kind of mature form in his joint book with Ackermann, called, by the way, translated in 50s already into Russian, which was basically textbook of say mathematical logic, but very new and original for the time. It's not quite standard according to today's usual treatment of these things, right? But so what he meant is just a kind of list of tautologies. Just remind, I think I mentioned to you, right, this thing about different axiomatic style, or I would say maybe formal style. Let me. It's called today in the literature like Gilbert style, and Gensen style. Did you ever came across this? No.
No.
No. So that refers to formal theories. Okay, formal theories. Yeah, and formal theory, in today's sense, what it is, it's say a list of axioms and certain rules that derive theorems from these axioms. So this kind of deductive closure under these rules we call a formal theory. So again, there is interesting debate whether such a notion of theory is actually adequate, right? And I personally think that it is not. And so there are some other proposals, for example, that we should rather identify theory if we're kind of serious about theories.
Deductive closure как переводится?
Ну как, дедуктивное замыкание.
Значит.
So deductive closure, it's everything that we can derive. So we have axioms are just kind of distinguished formulas. So we have a certain syntax, right, that usually is supposed to have kind of logical semantic behind. So we, at least part of this semantics is supposed to be fixed, and usually it's logical part. So we don't interpret what is a conjunction, what is injunction, what is negation, right? Because that is supposed to be kind of logical business. But we do interpret non-logical, sometimes called extra logical axioms, right? Now think about, maybe you're more familiar with, say, Zermelo-Fraenkel set theory, right? So you have axioms written with classical predicate calculus, right? First order calculus, classical. And in first order calculus, we have all these things, like we have quantifiers, right? And we have these logical connectives. And actually what they mean, it's somehow supposed to be fixed, right? That it's not for something, but that's somehow that this means any, that means exist, that's supposed to be fixed. But then we also have axioms like intentionality, pairing axioms, foundation axioms, whatever, right? And that's supposed to be non-logical, right? So set theory, yeah, that's also actually, in a sense, conventional. and questionable and debatable. All right. However, that is, say, standard view that set theory is not a part of logic, but something that we develop with the logic as a formal theory. Yes, and then we interpret these axioms. Now, in case of set theory, the story of interpretation actually becomes complicated. Probably you know about this so-called Skolem paradox, Loewenheim-Skolem theorem. No? Did you hear
Sorry,
about
what theory?
Skolem? Sometimes it's referred to as Skolem paradox.
No, didn't hear it.
No, but that concerns already, say, axiomatic set theory, so like ZF, even could be other versions. And what you certainly know about set theory, that there are like countable and non-countable sets, like there is this hierarchy of different cardinalities, stuff like that. But actually, Skolem proved that if you really go formal, right, then you can interpret all these higher cardinalities just using countable sets. So in a sense, you may kind of explain away all these higher cardinalities in terms of just countable, of being countable. Yeah, I think it's useful we mention it now because it's actually very much related to Hilbert formalism, even if not directly, this is already later, right? No, maybe a simpler example, you may look into paper published by Tarski. It's called What is Elementary Geometry? I think it's 1959. Okay, I'll look, I can put in our materials. And then he just formalizes, say, elementary geometry, Euclidean geometry, just with a few first order formulas. No, then he also gives several versions and studied some mathematical properties, which theory is complete semantically, which is not, and things like this, which is decidable, which is not decidable, right? Yeah, but that's the idea, right? That you have certain first order formula, and then you say, let's my variables in my formula say range over points, over things I would think about them as points. Yeah. Oh, by the way, there is an interesting shift, more specific, between this Gilbert 1899, right, foundation of geometry, because there, in order to formalize it properly, you would actually need some sort of type theory, because then he had, say, points and lines and the planes as different types, and that's interesting development that's of type theory, which today is more active in particularly because of say computer application, because when you do something on computer, you apparently just need this type distinction, right? You cannot formalize in this typeless way as say ZF is written, right? However, the mainstream development at that point, it was not into type theory. No, actually useful type theory were invented more recently, right? Even the idea goes back to Russell, actually, of type theory. However, such type theory which really can be used for, say, expressing, for representing mathematical reasoning, they are rather, say, recent. Probably Per Martin Löf personally should be credited just for that, because basically he invented, no, it's recent history, so it's a bit scary to say that someone say I'm saying wrong, so I don't give enough credit to someone. However, as far as I know, he's just the inventor of idea of dependent type, which is fundamental, that really gives type theory that kind of expressive power that make it useful. Okay, so these theories, like in Tarski, they are type free. Yeah, that's not typeless, type three. This is usual term, and that's of course make them very limited. However, you can do that roughly. in elementary geometry, you just think about, say, a segment as a set of points, which is bad idea by, there are many arguments why it's a bad idea. By the way, some of these arguments go back to Aristotle, and Aristotle physics, there is argument why you shouldn't think about a straight line as a set of points. But anyway, it's kind of formally possible. Okay, so all this, at least in some early form, was already here, right? All this idea that you have this formal theory on the one hand, which is somehow logical, right? Which is, comprises logic, which, yeah, that's why, in a sense, Gilbert is not described as logicist, right? But he, for example, beginning of this book, I say, I want to make all proofs purely logical. Whatever it means, yeah, you should, it's open for interpretations, of course, that kind of claim, but there is certainly something behind it, right? Yeah. But the second step has to do with, I would say, with making logic symbolic, right? Gilbert himself would describe it as axiomatization of logic, and just coming back to this Gilbert style and Gensen style, right? So what is Gilbert style? That's how he did that, right? So what he called logical axioms were, say, tautologies, and what we would say tautologies, say, of the set P, say, yeah, that's will be controversial, but this is excluded middle, right? So law of, sometimes it's Lamb, right? Law of excluded middle, and I'll come back to this when I talk about intuitionism, constructivism, because these people didn't accept. So he had, that's at least, I think it's 11 or something. There are, of course, different versions of this kind of, I wouldn't call them atomic, but kind of basic, right? Tautologies. And then you have in Hilbert just one rule of modus ponens. Well, then you may add also substitution rule, but in some theories, the substitution treated as a part of this deduction system, and some other treatment, it's treated as a meta logical rule. No, so just let's talk about modus ponens. Do you know modus ponens?
Yeah.
Yeah, of course, right. So you apply this modus ponens to your basic so-called axioms, logical axioms. An idea is that in that way, Hilbert proves that you may obtain, generate, if you like, right? Just using kind of language, algebraic language, all tautologies, right? So that's his idea, that that's how he did that. And that Hilbert style. But Gensen's style, Gensen was assistant to Hilbert, and Gensen is the author of, probably heard about natural deduction. It's a calculus, natural deduction, and sequential calculus. All right, calculus. And here, so he argued why it's actually, he called it natural, because he said, if we really think about logic kind of more practically, right, we never are concerned with such things, how we obtain new tautologies from some finite list of given tautologies, right? It's something maybe interesting from, say, meta-theoretical point of view, but it's very far away from any application of logic. But what we do in logic, we just follow certain rules. We know that there are certain rules. Rules, for example, for a rule, actually he put this rule in pair. For example, if you have P, you may obtain a P or Q, right? And that would be introduction. So it's intro, right? It's actually, there are two such introduction rules for disjunction, because you may also introduce it not that way, but that way, right? So there are two introduction rule. Then there is elimination rule. Yeah, for disjunctions, by the way, it's a bit involved. So maybe better, easier example is actually conjunction. So I give you example of elimination rule for conjunction, and that's if you have say conjunction, then you may derive P and you may derive Q, and that eliminates conjunction, right? So that introduces disjunction. So you have just a list of rules. Actually, you don't need axioms at all, right? So so you may just, so it's kind of system of rule that you may feed with certain, say, hypothesis and derive something. Or you may also feed it with some proposition that you may describe as axioms. You see, so roughly speaking, this Gilbert style, you have a lot of axioms and very few rules, just like one rule, modus ponens. And in Gansen style, you have a lot of rules and you might have not axioms at all. Yeah, so that's the difference. In many cases, they're kind of equivalent, but in some interesting cases, actually, they are not. Yeah, so that's yeah, and why I mentioned that, I mentioned that because it's all in Gilbert style. You have this kind of continuity between, say, formal theories, contental theories, right? Like theory of geometry or set theory, and pure logic. Even if, as Jaakko Hintikka argues, this is just kind of apparent continuity, that in fact, it's still very kind of essentially very different. But okay, I will not go to this example. I just, let me go back to, yeah, to my contents. Yeah, no, anyway, so he, on the second stage, he put into consideration, say, symbolic logic. He develops some systems of symbolic logic. First order in collaboration with Ackermann and in other places. And right, now at that point, even, you see, even if this foundation of geometry could be thought of as a kind of practically useful thing, right? Practical in the sense that even if this elementary geometry by itself was not very important, one could use this axiomatic pattern for doing something more interesting than elementary geometry, right? And many people did, even if it didn't always work very smoothly. So there were very interesting kind of difficulties when, for example, Ostwald Veblen just wanted to apply this method, say, for Riemannian geometry, right? So it didn't actually work in that way, in that kind of clear way. However, still it worked somehow, you may say. Yeah, but when he did all this more, say, logical research, then it's mostly became, we could say, meta-mathematical, right? So he didn't really produce some practically useful formalizations. And yeah, now just going to our time, I think it's only more recently, that we really somehow manage to formalize theories, to formalize, say, non-trivial theories, right? To formalize theories, to use this formal approach in outside mathematical logic itself. You see, there is this very interesting kind of controversy, because when people talk about mathematical logic, that's of course is highly developed and respectful subject, but it's as a matter of fact, it's much more about application of mathematics, of different kinds of mathematics to logical problems, right? It's much more than application, say, of logical approaches to mathematics in general. And only recently, I hope we'll discuss it next week. I'll tell more about, say, computer-assisted proof verifications, things like this. So Gilbert, apparently, he had in mind some applications, right? So he kind of imagined that people could bring papers which are kind of formally verified. However, it didn't work. And actually, he was concerned with rather kind of meta-theoretical problems. And probably the most, that was number 2 in his list, problem of consistency of arithmetic, all right? Consistency of arithmetic. No, by the way, also there is a lot of kind of historical, how should I say, mistake, because of course, consistency of arithmetic is a widely discussed topic in logical circles even today. By the way, Gensen provided a proof of consistency of arithmetic. That there is this very much popularized second incompleteness theorem by Kurt Gödel, right? That says that such a proof of consistency of, say, arithmetic cannot be done by arithmetical means. But if you look again into real history, there are interesting details. For example, Gilbert actually meant when he described this consistency of arithmetic. Sorry, does anybody understand what consistency means? Как вы переведете consistency на русский язык?
Последовательность, стройность.
Ну нет.
Совместность.
Вот правильно, нет. Смотрите, consistency — это то, что на русский переводится непротиворечивость. То есть у нас вот это слово сейчас, оно как-то с немецкого. Но вот по-английски consistency именно означает, ну вот в таком контексте, да, вот там логики, теории моделей, это непротиворечивость. Вот как-нибудь. То есть отсутствие формального противоречия. Что мы не можем там вывести А и вывести не А. Вот это именно называется consistency. Okay, so yeah, probably I should write it down somewhere, because you see, otherwise it may be really confusion. So consistency. Yeah, I'll tell now how this term is motivated, because right, etymologically consistency is something about what it consists of, right? I'll explain. But anyway, just boldly, I may say that consistency in that sense means непротиворечивость. Okay. So recall what Gilbert achieved in his 1899 book, on his book on Foundation of Geometry, right? As I told you last week, he proved consistency of geometry with respect to arithmetic, right? So it's called sometimes relative consistency. Относительная непротиворечивость. So precisely that means that if we think that arithmetic is consistent, right, then geometry, Euclidean geometry, is also consistent. And no, that could be too trivial, because probably nobody really doubted consistency of Euclidean, but that was not quite really in context of this discoveries of non-Euclidean geometry, right? Because real achievement, we might say, was that the same argument worked for Lobachevsky geometry just the same way as it did for Euclidean geometry, right? So in both cases, he produced what we would call today arithmetical models by thinking, say, about points as just pairs of numbers, and that you may do both with this parallel axiom and without it, right? So you get different models. However, both are consistent with arithmetic. And by the way, in that way, he proved that it's not possible to prove. So he proved independence of this axiom, right? So he proved in that model theoretic way, he proved that it's not possible to prove say parallel axioms from other axioms. Because if you just drop this axiom, right? So you have what Bolyai called absolute geometry. So geometry which is just kind of neutral with respect to just does have this axiom, right? Then you simply have different models, in some of which one is Euclidean, roughly speaking, and other models, no, the other model basically is Lobachevsky, right? Is hyperbolic. And then he does actually similar things with some other axioms, with Archimedean axiom. You can look, it's very interesting book, and it's easy to read if you have some background. Right, but that was all saying anachronistically, of course, model theoretic, right? So he proved this consistency of this theory, Euclidean geometry, non-Euclidean, Lobachevskian geometry, he proved by designing a model, arithmetical model. But then, of course, the next question is, if you're really foundationally concerned, so your next question is, what about arithmetic itself? How do I know that arithmetic is consistent, right? No, of course, kind of, there is an answer which probably is both commonsensical, but also maybe philosophical. I think it can be really justified. There are, say, serious epistemological arguments behind it that actually is kind of such a simple object, natural numbers, right? That probably we should take it for granted, because if we don't take it for granted, we kind of lose any ground, and then it's not clear at all what we are doing, what we're trying to justify by what, and so on, right? Yeah. So we cannot treat arithmetic in the same way. That's what Gilbert clearly understood. However, he believed that there is some different way to prove consistency of arithmetic. And that's exactly what leads us to this so-called formalism, right? So what was his thinking? His thinking was as follows. He thought that, okay, let's us do some symbolic theory of arithmetic, right? So we would do something like piano arithmetic that we do today. Then he actually used some other versions which are now more of historical interest. But just think about, say, do you know piano arithmetic, what it is?
Yes.
Yeah. No, you may look at the actions. By the way, Giuseppe Piano never produced it, as usual, right? In that form. Yeah, that's another very interesting figure and character. So that we don't have time to talk about him in this course. Yeah, but what we understand today by piano arithmetics is actually like they may a little bit different number. Is I think it's usually 5 axioms and one scheme of axioms for induction. All right. No, anyway, it's kind of symbolic calculus, right? So what was idea of Gilbert? How we can approach this wanted proof of consistency, we may simply forget about what this calculus represents. We may even forget that this is arithmetic or anything like that, right? That's what he's proposed. That's where, by the way, what you can read in literature that allegedly Gilbert tried to think about mathematics as a game of symbols. That's, of course, just wrong. It was just one particular approach, прием, как we would say in Russian, for solving very specific mathematical problem, right? Which was foundational, of course, which was very important in his view, but still, it was not how he thought about all of mathematics, of course, right? But now imagine that you have that sort of calculus, so you even forget what it represents, that it's about arithmetic. You may even forget this logical semantics. You may forget that these symbols, like what we usually use for conjunction and what you use for, I don't know, existential quantifier, what they really mean. They don't mean anything, right? They're just symbols. And so you have a kind of combinatorial setting, right? And then you have a rule kind of that allows you to generate new formulas. So you let's call this thing just formulas. You still have some syntactic distinction between well-formed and ill-formed formulas. Yeah, that is part of the symbolic game. And then you have your, say, substitution, and you have your modus ponens. So from some given formulas, you may obtain new formulas. Right. And then just try to think about this combinatorial system and let's study it by mathematical methods, say from outside. That's what he called actually meta-mathematics, right? Meta-mathematics. You see, so you have like two layers here. So you have a layer of just normal contentual mathematics, right? You're supposed to formalize it, right? So you express your normal mathematics in the symbolic language, right? But then for doing this mathematical research, you really just take it, this syntax as it is. You see, like bare syntax. So you just forget or kind of break it. It's semantics for a moment, just to come back, of course, but you just, for a certain point, you just forget about that. And then you're trying to solve this, what looks like normal combinatorial problem, whether or not it's possible using this kind of atomic given formulas and this rule for generating new formulas, whether it's ever possible to obtain expression of the form, say, P, and obtain expression of the form non-P. And so he hoped that for, yeah, sometimes, by the way, his position is also described as a finitism. I'll explain now in a minute, right? So that's where this idea of formalism comes from, right? Yeah, so he hoped to prove that, say, it's impossible. And that would mean that you obtain kind of syntactic proof of consistency, you see? So not by designing models, but by proving that, say, formal contradiction, that's combinations of formulas, is simply impossible in the given set. Of course, the next question is what kind of, how much of mathematics you need to prove it, right? Yeah. And here, actually, he was never very, say, definite. Yeah. Yeah, my French background comes, so I should. Yeah. Never definite, but his intuition was that all these kind of finite formulas, right? Even if that there is no kind of strong form of infinity. So there is kind of infinity because of quite obviously that's a, when we talked about this deductive closure, right? It gives us something infinite. We may apply this rule again and again, and there is, yeah, if we don't say limit lengths of our formulas, for example, right? It's quite obviously we may obtain more and more formulas, and that is unlimited, right? Yeah, and he thought that it's kind of simple thing, right? That it shouldn't, so we wouldn't need really strong mathematical principle, and we, most importantly, he was concerned about Cantor's set theory. By the way, he's one of his famous words. He has a number of famous words, but one of famous words is that nobody would expel us from Cantor's paradise, right? So you see, his position was kind of tricky, rather sophisticated. On the one hand, he wanted all these non-Euclidean geometries. No, just compare, by the way, here, probably you came across notion of Gilbert space. Do you know Gilbert space? Right? Like functional space.
Yes.
Yeah. So, yeah, so that's certainly not something very intuitive. So he really wanted kind of enjoy all these concepts provided by, say, set theory, some infinitely dimensional spaces, as he introduced himself, Hilbert spaces, right? All such things. Yeah. However, he was concerned about foundations. So he wanted to somehow ground that it's something which is clear and definite, and something that would allow to avoid mistakes, right? And that was the way his formalism kind of together with this finitism, that was his way, his program, as he described it, right? Hilbert's program to solve this big problem. You see, so he wanted to formalize all mathematics, roughly, right? Or at least show it's formalizable. That, by the way, important distinction, I think. However, yeah, it's kind of interesting to read more, maybe how exactly he thought about this. What happened in history, of course, that people just talk about formalizable and almost never about really formalized, until very recently, as I just mentioned. Yeah, so, but the idea was that after all, you may represent all these infinite dimensional spaces or higher cardinality or whatever have you, you may formalize in kind of finite formulas. Well, then, of course, there are again further issues. What is finitely formalizable, axiomatizable, what is not finally. Say in even piano arithmetic, you have not only axiom, but also scheme of axioms. But these are all important details, of course. But I just give you a big picture now, ignoring these details, right? So his vision was that after all, it's all kind of can be expressed with not very complicated syntax, with just one rule of generating more formulas from given formulas, which of course logically we interpret as, I say, logical inference. But now again, we may forget it, that it's logical inference, right? You just study syntax, bare syntax. And then he believed you wouldn't need really a lot of kind of complicated mathematics in order to prove, for example, this. You see, that was his so-called formalism. That's why formalism, and that's why finitism, because again, intuition was that on this mathematical level, you wouldn't need really notion of infinite. in any strong sense. So probably kind of a potential infinity that, by the way, even Brouwer, every constructivist would also accept. Even if you now study, you see that he was never really precise. Of course, what we have in today's proof theory, it's much more precision, it's much more refined. So, but Gilbert was in the beginning of this development already in his later book written jointly with Paul Bernays, which I already mentioned, right? It's called Grundlagen der Mathematik. По-русски это переведено, называется «Основание математики». Там первый том, это в 70-х годах. Я забыл, кто там переводил, по-моему, Нарский.
У меня отвлеченный вопрос: английский в каком году стал интернациональным языком там, до науки, статей и прочего?
Ну, видите, на это, наверное, даже и невозможно ответить, потому что такого момента-то какого-то не было тогда. Да.
Ну, в смысле, это было все после начала 20 века?
Ну, после войны, ну, конечно, конечно. То есть вот в эти годы, там, условно говоря, какие-то 20-е, да, 20-е, 30-е, то там на самом деле, ну, такое мультиязычное все. То есть из таких вот рабочих языков научных это немецкий, ну, может быть, он даже на первом месте, французский, но английский уже тоже. То есть уже английские публикации, конечно же, есть и какую-то роль играют. Вот. Ну, где-то русский, конечно, такой все-таки, он более сложный. Но вот Лобачевский там что-то по-русски. Ну, русский все-таки, конечно, такой, наверное, да, и итальянский, конечно, тоже много по-итальянски. Ну, нет, это интересный вопрос. То есть такое вот доминирование уже английского это после войны. После войны. Вот даже 30-е, ну, наверное, английского как-то побольше становится, может быть, хотя я не уверен. Ну, знаете, чтобы вот, так сказать, серьезно говорить про это, надо, конечно, такие вот уже исследования проводить, в том числе и количественные, просто вот действительно сравнивать количество публикаций.
Да не, у меня поверхностный вопрос был просто в целом понимать, там, почему они писали не сразу на английском.
Нет, ну, конечно, нет, у них даже не было таких точно совершенно поползновений писать на английском. Я, кстати, не знаю, знал ли Гильберт английский, то есть, скорее всего, он знал французский, все-таки это вот такой был тоже язык, который образованные все люди знали. А вот английский был, ну вот, ребят, могу сказать, вот мои бабушки, да, которые тут учились в гимназии, не в Питере, правда, а в Москве, вот они знали немецкий и французский хорошо, а английский вот они, так сказать, немножко изучали, это такая уже как бы дополнительная фича. Это вот как раз где-то в 920-х. А немецкий, английский, французский, немецкий, они как русский знали. Так что вот как-то так примерно.
Понятно.
Да. Ну, давайте я все-таки на английском буду, потому что может, кто-то посмотрит. Ну, собственно, один человек, который не знает русский, но тем не менее. Вот. So do you have questions about formalism? So that's roughly what this formalism and finitism works. Of course, there is a later story. Today, there is this big narrative with Gödel, who in 1934, right, proved his inconsistency theorem. There are actually incompleteness theorems, right? There are two theorems, I think you know, right? The first is about semantic completeness. Or should I say what is Gödel incompleteness theorems are about? No, I am not going to prove this, but maybe just who can give statements of first and second Gödel's incompleteness theorems?
I think we remember.
No, you remember, right? Right. Okay. So first is about semantic incompleteness, and second is about this consistency proof, right? It's well, it's a kind of strengthening of the first one. Okay. Yeah, and but actually in popular literature, in many philosophical, of course, there are very straightforward that say this Gödel's result kind of just made a blow, just stopped this Hilbert program. That's all wrong, of course, right? Because it neither. By the way, they discussed this result in this. I think it's 1934. It's first volume. First volume called Foundations of Formal Mathematics, something like this, and second called Proof Theory. By the way, the term was coined by Gilbert, proof theory. Right. So they discuss these results, and of course they are relevant, they are interesting, but it's just wrong that it's they kind of devaluate all Hilbert's efforts. Of course, there are also. I really recommend you a recent paper by Sergei Artemov. I think yeah, this paper. So Sergei Artemov is actually Kolmogorov's pupil and logician, and also he's doing computer science in the City University of New York. And he made this provocative, but I take it very seriously, argument that this usual interpretation of second incompleteness theorem is just wrong. Yeah, and of course he doesn't challenge Gödel's mathematical result, right? But he does challenge its standard interpretation, because in order to get from mathematical theorem to such a claim that, say, it's impossible to prove arithmetic by arithmetical means or something like that, right? Because it's not precise mathematical claim, right? You should really somehow identify what proof is, right? And usually, actually, after Hilbert, proof is simply identified with the formal derivation from axiom. But Sergei argues, and in my opinion, quite convincingly, that this is just wrong. Yeah, so I really recommend. So if you understand the proof a little bit more liberally, and actually this corresponds more or less to what we really call proof in, say, mathematical practice, then actually this argument no longer goes through. And so Sergei, if you like, he provides such a proof. No, I should say his proof is based on the idea that you somehow accept arithmetic intuitively, right? So it's more complicated whether it's really what is kind of epistemological value and meaning of his result, right, of his argument. So you may probably challenge it on epistemological, philosophical grounds. However, I think he's just right for saying you shouldn't, you may think how mathematical proofs can be mathematically represented, logically represented, right? But you just shouldn't take for granted one particular representation, and then whatever you prove about it, as Gödel did, then you just take it as a kind of philosophical truth. I think there is no such passage from mathematical truth to philosophical truth. So a more neat distinction between philosophical arguments and mathematical arguments is really needed. That's at least, that's my opinion about it. Yeah, okay, probably let me stop, otherwise I will not have any time to tell about other characters, okay? So there is a lot to be said about Gilbert. He's absolutely great. and still provides a lot of motivations and to historians, mathematicians, philosophers, and so on. So that's roughly what was formalism and finitism. Okay, that is usually attributed to Gilbert. However, let's look very briefly. Let's first into logicism, right? So logicism, why it's, you ask, right? What difference between logicism and formalism? So logicism is the thesis that mathematics is logic, okay? So Gilbert's formalism, Gilbert never claimed anything like that, right? That mathematics is logic. He rather even was inclined to think about this mathematical core, this finitistic core, as a really foundation, maybe also to logic. I'm not sure he was ever very explicit, but I actually, in my book and my dissertation, I have some quotes, some passages from Gilbert that at least support this point of view, even if not explicitly state. Okay, so that's idea, just the kind of provocative thesis saying mathematics is logic. No, so Frege again is a very interesting prolific figure, Gottlob Frege. He's important, of course, mostly in the history of logic, because he's more or less inventor of logic in that form that we study today, like first order classical logic, for example, right? No, actually, his project was limited to arithmetic. Frege did not believe that, say, geometry is logic. However, he believed that arithmetic can be fully reduced to logic, right? And Russell, for Russell, look to his book. It's called, it's 1903, called Principles of Mathematics. Principles of Mathematics is a book written is a kind of nice prose, and of course you'll see he's not really a mathematician. Yeah, sometimes it's said that he was not. He clearly was not mathematician, but it's kind of new vision of mathematics with some details and very strong, right? So his idea that mathematics is kind of formal tool. It's like logic. It's kind of set of principles and language. Then, of course, there is a lot of philosophical nuances. I have no time, but the idea was that it was all like logic. Now, I would say that, of course, if you are, how to say, to make any sense of such a thesis, right? You should, first of all, make clear distinction between, say, logic and mathematics, when exactly logic stops and mathematics starts, so to speak, right? And I should say there is no consensus view on that matter. So as a matter of fact, for example, at least some fragment of what we would call today set theory, every stuff about, say, classes, like extensional classes. Think about, I think you learn about proper classes, right, from von Neumann. It's usually mentioned. So for him, that was part of logic, right? And then, of course, so when it's said that he reduced or attempted to reduce mathematics of logic, you should also ask what exactly he understood by logic and what he understood by mathematics. And then, yeah. But anyway, that was his kind of claim. Frege did it with respect to arithmetics. And, probably you know the story about Russell paradox, because in already a late period of his life and activity, Frege worked what is usually known as Begriffsschrift, Schrift. So it's a kind of also symbolic calculus, literally calculus of concepts. And then he also used this kind of unrestricted comprehension axiom roughly, he believed that if you have some predicate, say P, right, then you may consider a class of all individuals that have this property P. And that's, you know, Russell paradox, I think, right?
Yes.
Yeah, and then Russell presented his paradox. In some description, it's kind of picture it as a really major event in all history. I don't think that's really correct, but anyway, that's part of the history. So that's this logicism, and well, I would say it's not quite on the same footing, because Gilbert was not mathematician, or at least not mathematician of the same rank as Gilbert and Brouwer. He also collaborated with North Whitehead, who was actually more mathematical. At least he did more mathematical. North Whitehead, not to be confused with the Whitehead topologist, who is younger. So that's his Whitehead of Principia Mathematica. He also wrote some rather peculiar philosophy. He was also a prolific writer, like Russell, but he also, for example, written first book on general algebra. It was very early, I can't quite remember, but about the same day, maybe very first decade of 20th century. So that was before van der Waals and all these people. So that was very new for that time. Yeah, and together they produced also 3 volumes, and a big part of that actually Russell did in prison, because he was in prison, and the reason was he didn't want to go to war. And interestingly, he was actually imprisoned second time already in the United States, and also for kind of pacifistic activities when he was protesting against war in Vietnam. It was, I think, in 1961, if you can check. So he was twice in his life in prison. Then I think he was about a year or more in prison. Yeah, and that's kind of their version of Begriffsschrift. It's something absolutely unreadable. By the way, I think it's translated finally into Russian. Some enthusiasts did this. It's written almost like computer code with some commentary. All right, and but apparently it didn't have any influence neither on logic or mathematics. Maybe I'm wrong. Maybe some logician read it, but very few people, I think, have read it. In a sense, it's a kind of curiosity. Yes, but otherwise, they both, in Russell and Whitehead, wrote very nice English prose, and a lot of it, particularly Russell. Yeah. By the way, he was given Nobel Prize for Literature for books about relationships, about sexes. He was kind of against family. He was kind of early kind of left activist, but also he was the gay, very much criticized, say, Soviet project, Bolsheviks. So he was really very interesting person, and who lived, if I'm not mistaken, until 96 or something. He died in that age. So it's absolutely fantastic personality. Okay, that's probably I should stop for us, but he was never a mathematician like Gilbert or Brouwer. And now let me, in the remaining 15 minutes, say a couple of words about Lutz and Brouwer and his engagement with Gilbert. So Brouwer is a Dutch mathematician, right? Who actually kind of oscillated between mathematics and philosophy. It looks like, okay, maybe just my judgment, he was much more talented as mathematician than as philosophers. But still, he did his PhD in philosophy, not in mathematics. I tried to read it. It really is kind of strange. Basically, it's kind of Kantianism in a new form, right? Usually, he's not called Neo-Kantian, but basically, he followed Kant's line, but trying again to combine it with this all new mathematics that he knew. In pure mathematics, he had the achievement absolutely outside all this foundational business and philosophy. So he proved two big theorems. One, probably you know, it's called Brouwer fixed point theorem. So it's about continuous transformation, say, of a closed disk, say in Euclidean space or something, right? It states it has a fixed point, the theorem states. And second big theorem was about invariance of topological dimension. So if you describe dimension, say topologically, no, okay, I will not elaborate, but so not metrical, right? Not metrical dimension, but really topological dimension. And then it was discovered even by Cantor that say it no, say set of points in three-dimensional space, it's the same continuum as say on one-dimensional line. And even for Cantor, that looked kind of weird, right? So what Brouwer actually proved, he proved that if you not talking about just one-to-one correspondences, I'll say unspecifically, but if you require that all your correspondences are continuous, right? That those are continuous transformations, then this there is no such continuous transformation from line to say three-dimensional space, right? So the notion of dimension topological is invariant with respect to continuous transformation. No, that kind of makes sense. In my view, it even saves set theory. If this wouldn't work, just one could say that it just kind of wrong doctrine, all this set theory. So, but now it makes more sense. Say, yeah. So I think, yeah, and these theorems were the first fixed point theorem was probably related to his say philosophy of mathematics because it was not constructive. Oh, by the way, maybe you know, if you have this more specific Banach theorem, right? If you have your transformation which kind of shrinks, как это называется, сжимающее отображение, then you may constructively determine your fixed point. However, in general case, it's not constructive. It's purely existence theorem. And I think that really concerned Brouwer. In a sense, he might not believe his own theorem. And there are indeed, so he developed this so-called intuition. So his so-called intuitionism is actually a mixture of many different things, right? So there is kind of Kantian, his version of Kantian philosophy behind it, which he actually reserved to arithmetic. So his idea was that, okay, in geometry, we cannot save this approach, right? However, we can still think about arithmetic as a kind of basic human intuition. So, and he introduced some interesting notions with which he really described it, right? And he really believed that these non-constructive proofs are somehow wrong. Yeah. Do you know this example? It's not from Brouwer, but I don't know who invented it. So question is, are there two numbers? So question is this, are there A, B, no, real numbers, and say, how I should put that way, right? Irrational, right? So, or what should I put? Yeah, no, I think that side, right? Irrational, so they're irrational, such that A to B is rational. Do you know the argument?
No.
No? Yeah, no, no, it's kind of almost joke. The argument is just take A equals B equals square root of 2, right? And okay, now you have a square root of 2 to square root of 2, okay? Now, if I remember. So it's either rational or irrational. Okay, so case 1, let's call it C. C is rational. Then we are done, right? So that's example. So case 2, C is not rational. Is not rational. Okay, if C is not rational, just consider C2 square root of 2, right? And that gives you what? It gives you square root of 2 to 2. It gives you 2. So you're again you found different. So you are done. You see? So yeah. So just using excluded middle, and we use the excluded middle when we distinguish these two cases, right? We proved the theorem that the answer is yes, positive, but without providing any real example, right? So we still don't know whether this thing is rational or irrational. But if we use excluded middle, we don't know, we don't need to know it, you see? And that, of course, looks like very much as a kind of cheating, right? Even if argument is okay, assuming we somehow justify the use of excluded middle. I think it's just a good example for kind of motivate this constructive program, say, no, we just shouldn't do such tricks. It's something, it's not real mathematical proof, it's kind of cheating. Yeah, so, and so he designed the whole program of kind of puring classical mathematics, including calculus, differential integral calculus, from excluded middle, right? He invented, it's rather interesting and specific. There are some, we have absolutely no time to go to that. It's rather specific. He invented some special concept. It's one called spread. I think there is spread, and there is also fan. It's all about kind of infinite sequences. Yeah, the most basic is called choice sequence. Choice sequence. So intuition is that we.
I don't understand why C in power of square root of 2 is equal to the square root of 2 in power of 2.
Here?
Yeah.
No, if you square root of 2 to square root of 2, right, and you square root of 2, then this you multiply, right? Yeah, so you just get to, yeah, it's just school arithmetic. No, it's here. It's clean. It's there is no. Yeah, but then no, I think it's rather appealing. It's not his example, but I think it's example where if you want to say that this pure existential theorem, there is something wrong about them. I think it's a good example. That real work is just to say whether that is rational or I think that was solved, but that's not easy to solve, right? To say it's rational or irrational. It's non-trivial, and that's something completely trivial, and it gives you answer without really giving any example, because yeah. Okay. Yeah, so there is a kind of specific mathematics, and he kind of aimed at rewriting analysis, and actually people somehow didn't really like it because it's, for example, this theorem about intermediate value, if you have a function, right? Of course, continuous function, right? And one value is negative, another positive. So the theorem says it somewhere at zero. It's also non-constructive. It's something like this. So you need, you cannot easily prove it without excluded middle. And if you want to do something similar, to replace it by something without excluded middle, then you need to really introduce the whole bunch of new concepts. So no, I actually once followed semester by there is a, he's in Moscow called Plisko. He's a specialist in, I forgot his first name, Plisko. You may look. No, it's described in many, but it's very peculiar, of course, right? It's kind of almost curiosity. Even some people are more serious probably about that. But I don't know if you have another 5 minutes. It's okay, or you? It's my question.
Well, actually, I don't sure.
You need to switch to something else, right?
Yes.
No, okay. Probably I'll finish next week just a little bit about this. That will bring us to more recent. Okay, let's then stop here. I continue next time with Brouwer, with this constructivism, intuitionism and stuff. Okay. Так, ну, все тогда, всего хорошего. Значит, еще раз, ребята, давайте все-таки постарайтесь презентации сделать, чтобы у нас не получилось, что никто не готов делать презентацию. Ну, вот готовьте на через 2 недели.